Hi there. In this video, which is the second video in the Chapter 1 material, I'm going to finish out the conceptual type of information that is in Chapter 1. I'm going to save the math and problem-solving related material for a different video. But let's go ahead and continue on and finish up the more conceptual definition type of material that's covered in Chapter 1. All right, so remembering to take notes into your notebook. The next thing I want to talk about is physical versus chemical changes. So this is another one of this Chapter 1 material that is really not the most exciting material, but is actually quite important to make sure that you're framing things in your mind correctly before we proceed on to kind of layering more information into your knowledge of chemistry. So what's a physical change? What's a chemical change? How are they different and why does it matter? Let's go ahead and start with physical changes. So a physical change changes only the state. And remember, the synonym for state in chemistry is phase. So I'll just put that in parentheses. Changes only the state or appearance of matter. So let's start with the first part. When we talk about a physical change, one type of physical change only involves changing the state of the matter. So essentially, remember, there's only three states of matter. There's solid, there's liquid, and there's gas. Those are the only three states of matter that exist. And you can change one state into another state really by changing two different things. The first is the most obvious, is that you can change the state by changing something's temperature. That's what happens when you take water and you put it into a freezer. You lower its temperature, and that's why it goes from a liquid to a solid. A lot of people are perfectly familiar with that, but the other thing that you can do to change the state of a substance is to change the pressure that you're putting on the substance. Picture probably the most easy example to understand is what you use for gas grills, which is called liquid propane. Propane is normally a gas, okay? So if you picture a gas, remember we talked about that the molecules are really far apart, a gas, when they're a gas. If you take a sample of propane gas and you squeeze the container, what you're doing is you're essentially pushing those molecules together. Okay? If you change the pressure, if you raise the pressure on the sample, you push the molecules together, and you will turn a gas into a liquid. And if you push them farther, you would turn them into a solid. So that is the other thing that you can do to change the state of matter. Let me just find my eraser. Let me give you something to write on your notes here. Let me give you this. By changing, and by the way, let me introduce this new thing. This little triangle is a Greek letter delta. It's a triangle. And it is in math and science used often to substitute for the word change. So in shorthand, you can write that to mean changing. By changing temperature or pressure. Those are the two things that you can do to change the state of a substance. But anyhow, let's get back to this here. If you go from a solid to a liquid, that has a name. And we're familiar with the name. Going from a solid to a liquid is melting. Let me go ahead and give you another, maybe somewhat new thing here. Another word for melting in chemistry is fusion. Fusion. Those mean the same thing. Fusion or melting. If you go from a liquid to a gas, that is called, you know it, evaporation or vaporization. I'm going to write vaporization. vaporizing. It's the same thing as evaporation. You really can use either one. To go backwards from a gas to a liquid, that is called condensation. And if you go from a liquid to a solid, you know it, it is called, what you call in regular life, freezing. There actually are two other phase changes, much less popular. Let me erase this here so I can get some space. Let's just go ahead and give it to you now, why not? To go from a solid to a gas, okay, without passing through the liquid phase, to go straight from the solid to the gas phase. That can happen, that does happen under certain conditions, and that is called sublimation. Sublimation. And the opposite of that, to go from a gas to a solid, is called deposition. D-E-P-O-S-I-T-I-O-N. That's probably the least famous of all the phase changes. Oh, and by the way, all of these, 1, 2, 3, 4, 5, 6, these are all called phase changes. That's a good chemistry term. You're going to use that a lot, especially when we get into the thermochemistry chapter. Phase changes. All you're doing is changing the state of the matter. Now, we can write that in a very kind of chemistry way. Let me go ahead and write for you the melting of ice in a very chemistry, in kind of like a chemical reaction type of way. So the melting of ice would be H2O, solid. Remember, that's the phase label for ice. Solid water becomes H2O liquid. That's how a chemist would write the melting of ice as kind of a chemical reaction. Well, it's not technically a chemical reaction, but it's kind of how a chemist would write this phase change. Here's what I want you to notice about this here. The substance itself does not change. What used to be H2O is still H2O. In other words, the chemical bonds that hold these atoms together are still present on the other side of this phase change. None of the atoms separate, and none of them get recombined with anybody else. H2O stays H2O the whole time. The molecule is still intact. The only thing that's different is how one molecule is relating to another. Are they far apart like a gas? Are they close together like a liquid but able to slide past each other? Or are they in fixed positions like a solid? That's really the only thing that's changing. All right, that's a physical change. And for the most part, when people talk about physical changes, they're talking about phase changes. There is another, actually, let me say one more thing here. Because all you're doing is changing temperature or pressure, and you're not breaking any bonds or whatever, one of the things that I want you to write is that phase changes are reversible. All you have to do is revert back to the original temperature or the original pressure, and you'll recover the original state. If the water has frozen because you put it in the freezer, take it out of the freezer, put it back on the counter, and now you go back to a liquid. You can just reverse it by just kind of reverting back to your original temperature or pressure. All right. Appearance. This is the other kind of word that we want to address real quick. This refers to something like hammering a metal. When you hammer a metal, if you were to hammer a nail, you will change its appearance. It will get more dull. You would actually, maybe you could bend it just by hammering it. You're not actually changing the atoms. You're just changing the way that they relate one to another. So this would be just an example of changing something's appearance. It's not actually messing with the atoms or chemical bonds. It's just how the atoms relate to each other or how the light is reflecting off of them. All right, so that's just kind of a little small aside. But for the most part, physical change, think about phase changes. Let's come over to chemical change, because this is the big difference here. When you have something undergo a chemical change, it's quite a different situation. I know what maybe you could say here. Maybe write in your notes, nothing new is made. That's a good thing for you to write. Nothing new is made with a physical change. That's going to be contrasted over here. So now let's come over to a chemical change here. When you have a chemical change, a chemical change alters the composition of the matter, whatever matter you're talking about. Let me go ahead and do a semicolon here. How does it alter what the matter is composed of? This is what happens. If something undergoes a chemical change, atoms, or let me actually start like this. Chemical bonds, the things that hold atoms together, chemical bonds are broken, atoms rearrange, and new bonds form. And that results in a new substance. Okay, something new is made after a chemical change occurs. Coming back to the Lego example, it's kind of a chemical change. If you think of the atoms as Legos, you have say a molecule. To make a chemical change, you have to break what you have. Okay, that's breaking the original bonds, rearranging the Legos into something new, a new Lego creation, forming new bonds by pushing them together, and that represents a chemical change. So you have something new, a new creation on the other side of a chemical change. Let me go ahead and give you an example. There are a million examples because truly what I'm describing here with a chemical change, let me write AKA. AKA means also known as. This is also known as a chemical reaction. A chemical change is a chemical reaction. They're the exact same thing. So let me go ahead and write for you just a chemical reaction that can help us illustrate what a chemical change is. I'm going to go ahead and this is your very first chemical reaction in this class. So 4, let me make that look more like a 4. 4 Fe. So hopefully you're starting to memorize your elements. And hopefully at this point, maybe you're getting to that point that you have this quick. That is iron, and you should know that soon. 4Fe. Now I'm going to write the phase label here, solid. This is, by the way, something that I'm not expecting you to memorize this or to have been able to come up with this on your own, nothing like that. But if I was to give it this chemical reaction to you, we're going to kind of go over what the parts are and how you can, call different things. So 4Fe solid plus 3O2 gas. Get some new space. Arrow. And I'm going to teach you how to say all this in just a second, but let's get it in your notes first. 2 Fe2O3 solid. Okay. All right, what you're looking at here is a chemical reaction. Okay, so now we're kind of getting into kind of real chemistry here. All right, let's go over what all this business means, because you're going to start to kind of absorb this little by little as we get through the chapters. Anything on this side of the chemical equation, okay? Anything to the left of the arrow. And by the way, it's got to be an arrow, not an equal sign. It's an arrow. Forward facing to the right until you get to Chem 102. Then we'll start introducing backward ones too, but just to the right for this class. These are called reactants. Reactants are, let me write this, are the chemical species. And by the way, we use that term species a lot. It's a good word. Basically, it's just any guy in the reaction. This is one chemical species. This is another chemical species, the O2. This is another chemical species, Fe2O3. It's just like an individual compound or element, whatever it might be, but it's a chemical species. It's like a guy in the reaction. The chemical species before the reaction occurs. Those are what are called your reactants. That's what you have at the beginning. If you have a plus sign, what that means is that this reacts with that. Okay? So now we're at the arrow. The arrow means a chemical reaction is occurring, which means these bonds are going to break, new bonds are going to form to make something new. And you'll see this is the new thing that's made here. When you see an arrow, you can use a bunch of different words. To form. So this reacts with that to form. You could say to yield. You could say to produce. There's a bunch of different things you could say. It all means the same thing. But that's what the arrow means. So 4 iron solid reacts with 3 oxygen, okay, or you could say O2 for now, gas, to produce 2 Fe2O3. We'll learn how to name his name in due time, solid. Now, on the other side of this is called, in this case, there's only one product species. There could be 2, there could be 3. But anything to the right of the arrow are called products. These are the chemical species that you have after the reaction occurs, kind of like the end result. Like I said, in this one, there's 2 reactants or 2 chemical species for the reactants and 1 product, 1 type of product. It doesn't always work like that. Sometimes it's 1 becomes 3, sometimes it's 2 becomes 3, 3 becomes 5. It just, there's a million different things. It doesn't have to be a 2 and a 1. So that's reactants, arrow, products. That's what I wanted to introduce here. We will learn more about this now, but let me just go ahead and address this here. What we have, let me use this as an example. We talked about this in the last video. If you see a subscript, that means that in this chemical species, there are 2 oxygen atoms. So if you had to draw it, we'll draw 1 oxygen atom here. Let me make that the O, and I'll make the circle this. That's 1 oxygen atom. Here's another oxygen atom. And they're bonded together. Okay, that's what that is. This thing here is called a coefficient, and that's telling you how many copies of that chemical species there are. So if I say 3O2, that means I've got this, but 3 times. So in total, there's actually 6 oxygen atoms there. There's 2 oxygen atoms in each of these molecules, but there's 3 copies of them in the chemical reaction. If you're kind of quick with this, you've already noticed that this equation is balanced, which we're going to learn how to do later. But let me just mention it. There's 4 iron atoms before the reaction occurs. Over here, because this chemical species has 2 iron atoms in each one, but there's 2 copies of it, there's still 4, okay? And over here, there are 6 oxygen atoms before the reaction. And at the end, in each chemical species, there's 3 oxygen atoms, but there's 2 copies of it, so there are 6. So chemical reactions will always be balanced because the atoms don't disappear. They just rearrange. They just change partners. Like for here, the oxygen used to only be bound to another guy here, but now it's going to be bound to some irons as well. So it just kind of is, it's like a new creation of atoms. All right. So that's what a chemical reaction is. What you have, the key thing here is you have something new formed. Something new formed. Unlike the H2O solid going to H2O liquid, there was nothing new, just a new phase. This is totally a new species, a new chemical species is formed. Let's go ahead and just say a few things, more bullet points about this, and then we'll move on. Chemical changes are generally irreversible. Irreversible. Okay, once it's done, it's done. If iron, oh, by the way, this is the rusting of iron. Iron combining with water, or sorry, with Oxygen, this is just kind of like the most basic way of describing the rusting of iron. This here is actually, the term is rust, like the English term for this compound is rust. As you know, you can't really reverse the rusting of iron. All you can do is scrape it off, but you're not really reversing it. So this is a good example of that chemical reactions are usually irreversible. But there's another thing that I'd like to say is that they are often accompanied by a delta. So delta meaning change in color. Usually, or at least many times, chemical reactions result in a new color appearing because it has to do with the fact that the way that we perceive color is how light interacts with the atoms. And so if the atoms rearrange and have new arrangements, they will oftentimes reflect light in a different way. So that's what this is all about. As you know, iron is black, rust is orange, reddish, brownish. So this is a good example of that. All right, moving on to the next topic. That's enough about chemical versus physical changes. And this is still, in a way, I'm still kind of really just introducing this stuff. We will redo balancing chemical equations, naming compounds. All of these other things are going to get really taught slowly in later chapters, in like chapter 3 and 4. But this is kind of, you need to have a little bit of intro as you're learning. All right. Physical versus chemical properties. This part won't take quite as long. Physical versus chemical properties. All right. A physical property. A physical property can be observed. By the way, a property just meaning like a characteristic. Characteristic. Like a description, okay? A physical property can be observed. W/O is just my shorthand for without. Okay, I'll start using some shorthands just to make note-taking faster and teaching faster. Can be observed without undergoing a chemical reaction. And RXN is reaction, okay, chemical reaction. So if something is a physical property, you don't need to do a chemical reaction to observe it. You can just observe it without any chemical reactions. Let me give you examples because it will help understand. Color is a physical property. I can observe that this board is white without doing a chemical reaction on it. I can observe that my shirt is blue without undergoing any chemical reactions. It's just a plain old observation. Another physical property is density. Density. We are going to learn about density a lot in your first on-campus lab, but let me just kind of give you just real quick what density is. Density is simply a quick little calculation. Density is mass, which I'll do little m, over volume, which capital V. So if you can get something's mass and you can get something's volume, how much space it's occupying, you can just throw it into your calculator and get its density. And hopefully you can see that would be a physical property. I can get the mass of this marker by weighing it. That's not a chemical reaction. I can get its volume by measuring it in a bunch of different ways, which we actually are going to do in the lab. How much space it's occupying, I could just measure it and then put it in my calculator, and now I have its density. So that's definitely a physical property. So color and density, but a few other very famous physical properties, MP and BP. MP meaning melting point. And you guessed it, BP meaning boiling point. Oops, boiling point. Let's just review this real quick, or maybe introduce it real quick. So melting point, by the way, points are temperatures. When you hear melting point, you should think it's talking about a temperature. A melting point is the temperature at which a substance melts. For water, let's go ahead and give you that right now, because I think most people know this. For water, the melting point in Fahrenheit is 32 degrees. That's what we use for weather and in our culture for, you know, various different things. In science, we're only going to do Celsius. So really we're not doing Fahrenheit, so only Celsius. In fact, that's the only one I'm going to write on the board is the Celsius melting point, and that is 0 degrees Celsius. That's the temperature at which water melts. The boiling point is the temperature at which a substance boils. And for H2O, not worrying about Fahrenheit, only Celsius, it's 100 degrees C. So you can see how easy the Celsius, in fact, this is maybe clues you into the Celsius scale. The whole concept of Celsius is arranged around these very two important temperatures. That's why they fixed 0 for the melting, 100 for the boiling. Okay, they did that on purpose when they came up with what Celsius means. It's a man-made thing. All units are man-made. All right, so these are just two more physical properties. So those 4 are good ones. I'm sure there's others, but that's the only ones that we'll list on the board. Chemical properties, in contrast, can only be observed. Oh, actually, you know what? Let me back up just for a second. Why are these physical properties, melting point and boiling point? The key is you can determine something's melting point just by melting it. And that is not a chemical reaction. See, remember, that's just a phase change or a physical change. So all you'd have to do to find something's melting point is have a thermometer, melt it, and record what temperature did it start to melt. That's very simple. That's not a chemical reaction. So that's why these are called physical properties. Chemical properties can only be observed through a chemical reaction. So these properties reveal themselves only during the course of a chemical reaction. Examples, corrosiveness. Corrosiveness is basically the wearing away or the decay of a metal. And let me go ahead and give you usually by oxidation. Believe it or not, in a few more chapters, you will know what that means, oxidation. If you don't already know, we will teach what that is. But that is something that, it's a chemical reaction called a redox reaction. We will learn it later. But you're only going to know if a metal is corrosive if you see it corroding. Okay, so that's the idea here. So corrosiveness, another one, flammability. If I have a particular cleaner in my closet, Windex or whatever, and I want to know if it's flammable, I mean, I'm not going to do this, but the only thing that you would do is set it on fire and see if you see a flame. So that's a chemical reaction. By the way, burning is always a chemical reaction, always. So burning is always a chemical reaction. So that's another example of a chemical property. And another one would be acidity. How do I know that a particular substance is acidic? Well, you really only know that if you let it undergo an acid-base reaction and kind of observe that happening, which we will also learn in this course. So anyways, those are just examples of physical and chemical properties. And then the last part of this video is just a little bit on energy. Now, we are going to spend a whole lot of time on energy when we get to chapter 7, which is called thermochemistry. That's the whole chapter is about or endothermic, exothermic, heat flow, and all this other stuff. So, but energy is so important to chemistry that we have to have some basics at the beginning. And I will start to incorporate just discussing energy even in these early chapters. So let's give you now what you really need. And this, of course, is what the book does as well, because, you know, the author agreed that, you know, it's obviously an important thing at the beginning of the book. So energy. What is energy? Okay, well, if you think about the natural world, there's only two things in the natural world: matter and energy. So we've discussed matter. Everything's made up of atoms and, you know, all that other stuff. Has mass, takes up space, all these different things. Energy is the other thing in the natural world, okay? So energy is kind of like the other component. It's not matter, although it's related kind of in a very interesting way, but that's kind of beyond us for now. So let's just go keep it simple here. What is energy? Energy is the capacity to do work or to produce heat. All right. So, and all substances have a certain amount of energy. This marker has a certain amount of energy in it. I have energy. My glasses have energy. The air in the that I'm breathing has energy. So matter kind of has a certain amount of energy. Capacity to do work or to produce heat. Let me just give you what work is. Let me just give you what work is for now. Work is basically a force being applied over a distance. And that seems a little maybe hard to understand, but when I think of work, I literally just think of this guy pushing this box across the floor because he's applying a force over a distance, and that is what work is. Now, we apply that to other things besides a guy in a box. You know, we start thinking about atoms and things like that. It changes the way you think about it a little bit, but that's technically what work is, a force being applied across a distance. So we'll leave that alone for now. So that's what energy is. Now, most people know that there are two forms of energy. Okay, there's only two forms of energy, and the first is PE, and the second is KE. And I bet you that many of you, 90% of you, already know what these are. PE, say it out loud with me, potential energy. There you go. So potential energy. And KE, kinetic energy. All right, so these are the two forms of energy. Let's give you just a little bit about each one. Potential energy is the energy that is associated with really two words, both work, but position or composition. And by the way, energy is just hugely important to chemistry. So we do want to stay on this just a little bit because once you understand, you have to really understand energy to get chemistry. But anyways, let's talk about these two words for a minute because I don't want you to just think of them as like these nebulous words that mean nothing to you because they actually make a lot of sense. Potential energy associated with position. Let's start on that first. When you think of that word, I want you to think about me holding my marker up in the air. Okay, this is my black marker. Okay, so here we go. When I change the position of my marker and I lift it up higher, I have just given it more energy because, and that will be revealed because as you drop it, it's going to move, it's going to have more energy kind of released and you can see the energy come out when I drop it. It will fall harder if I've dropped it from up high than it will if I drop it from down low. So my point is that here it has a certain amount of energy, But if I change the position, it has more energy because it's against gravity even more, and now it will have more energy. So it's the energy associated with where something is in the universe, the position of it, okay? It does change. It has a different amount of potential energy. And by the way, it's called potential because the energy is there, it's in it, but you can't see it until you kind of like allow things to happen, or you remove yourself from it, and then the energy comes out. That's why it's like potential. Associated with position or composition. All right. Whoops. So the position is kind of just changing the where it is in the universe. Composition is a little bit more how chemists think about potential energy. This is how like physicists think about potential energy. Chemists, I prefer this word, composition. Let me go ahead and explain why. For a chemist, like you and me, we think about, it's a type of potential energy, and it's called chemical energy. We think about chemical energy. It's a type. That's why I'm writing it under here. It's a type of potential energy. It's the type that's associated with what something is composed of, what's in something. So for a chemist, we think about chemical energy, which is basically the energy inside, kind of trapped inside atoms and molecules. Atoms and molecules, which basically make up all matter, they have energy in them. And it's kind of mysterious because you can't see it until it comes out. Let me give you an example. Octane, okay? Let me give you this little nugget here. Octane, if you think about where have you heard that term before, you'll realize you've heard it from gas stations, high octane gas or whatever. Octane is a molecule. You can see what number is in there, OCT. What is that number does that make you think of? 8, like an octagon or, an octopus or an octahedral or whatever. So this molecule is C8H18, octane. That is the main component in gasoline. That's the main fuel in gasoline. This molecule, when you burn it, when burning it means you're reacting it with something. If you burn something, you are reacting it with something in the gas, in the air, and it is, many of you would know this probably already, you're reacting it with oxygen. That's why you smother things to stop them from burning. You take away their oxygen. It's actually the second reactant in the burning. When you burn octane, there's a chemical reaction that occurs, okay? I'm not even going to balance it, but it basically turns the octane, when you react it with oxygen, it turns it into CO2 and H2O. I'm not going to worry about getting the balancing right with the coefficients or whatever. These are just the chemical species for now. But hopefully you realize that when you burn octane, you release a whole lot of heat energy. And that heat energy is exactly what pushes the pistons in your car to make it move. So my point is that the car is just not moving randomly. The energy doesn't come from nothing. The energy was inside those bonds. It was in the molecule. You couldn't see it when you're at the gas station pouring out the gas or whatever. It doesn't look like there's a lot of energy there. It just looks like a liquid. But it's there. The proof is in the pudding. When you burn it, all that energy, and you change the way the atoms are arranged, all that energy comes out in the form of this massive amount of heat energy. And it goes and it, through the motor, will end up pushing your car, driving you down the road. The proof is in the pudding. All of that energy was in there. And that's what we talk about in chemists when we think about potential energy. That's what I think about. It's the energy in a molecule that gets released during chemical reactions. That's kind of how I think about it. All right. Let's go to kinetic energy. Kinetic energy is the energy associated with motion or movement, whatever word you like. It is the energy associated with motion. Let's go ahead and the way a physicist would think about that would be the car moving. Okay, the car moving, it's moving, that's kinetic energy. How a chemist think about it, let me go ahead and give you it like this. Chemists think about a type of kinetic energy called thermal energy. Thermal energy. Thermal energy is a type of kinetic energy. That's why I'm writing. It's kind of like the equivalent to the chemical energy being a type of potential. Thermal energy is a type of kinetic, and it's the type of kinetic energy associated with temperature. And this is very kind of simple. If you have, let me just give you room temperature H2O, room temperature water, okay? You've got the molecules, and they're moving. Okay, they're moving, they're sliding past each other and they're moving. If you go ahead and you heat that water up to, let's just say 80 degrees C water. So I'm not going to boil it because that will complicate things a little bit. But let's say I heat it up. What happens is that they are moving faster. And most people know that. I mean, I don't know how to write that with the arrows, but the molecules move faster. So there's more movement at higher temperatures, okay? And that's exactly what we're getting at here. The thermal energy increases at higher temperatures, which means they move faster. And they do. And as you cool something, they move slower, okay? So that's the type of kinetic energy that a chemist will usually be thinking about as thermal energy. 2 more things to say about energy, and then we'll be done with this video. First is, we'll make it a bullet point, is what we call the first law of thermodynamics. Okay, once again, if I'm using the term law, this is just something that nature obeys all the time. See, nature is much better than humans. Humans don't obey all of our laws all the time. Nature does. That's really good. So there's these, scientists have known this since people started studying nature, is that nature seems to obey certain laws all the time. And this is such a famous law that they called it the first law of thermodynamics. It's never been broken by the natural world, okay? So that's kind of how you want to think about that. It would take a supernatural event to break a law of nature. So first law of thermodynamics. This one here is also known as something even more famous, also known as the law of the conservation of energy. It's the exact same thing. And most people already know this by heart, the law of the conservation of energy. Let me give it to you on the board. Energy, let me just write it like this. Energy can neither be created nor destroyed. Okay, that's the first thing that you could just say that. Energy can neither be created nor destroyed. But there's an add-on to that I think is really helpful. It can only be, number 1, converted between types. Okay, I just gave you several examples of that. Potential energy being converted to kinetic, and then the car's chemical energy being converted to kinetic. So it can be converted between types, or it can be transferred between substances. So that's another example of that here. I just said that this marker got more potential energy when I lifted it up. But understand, I'm the one who gave it to that. And how did I do it? Through my own kinetic energy. See my movement? So kinetic energy gave this potential energy. So actually this is both, converting between types and transferring between me and him. Okay, so that's a transfer between substances, so to speak. So this is the law of the conservation of energy. But there's one other thing that a lot of times it's also said as, and that's this, or the total energy in the universe is constant. If you think about it, that's saying the exact same thing, because if you can't create or destroy energy, that means there's a certain amount in the whole universe that never changes, because you can't make more and you can't lose what you already had. So this is actually saying the same thing as that, but it takes a little bit of thinking to understand that it's the same law. So these are two different forms of what's called the first law of thermodynamics. And then the other thing that I would like to put on the board, and this is where we'll finish up, bullet point number 2, is substances, which, remember, is just our catch-all phrase for any type of matter. Any instance of matter could be called a substance. Substances always are driven to lower their energy. There's a natural direction for all of matter. Matter wants to calm down. Matter wants to chill out, okay? There is a reason why this marker, when it's high energy up here, there's a reason why it doesn't naturally fly up higher. If I remove myself from the situation, it will always lower its energy. It doesn't raise its energy on its own. It will always naturally want to lower its energy. There's only one direction that matter wants to go in, and that's from what we call, let me give you this last term, what we call a high energy. And in chemistry, this is a great term used quite a lot. Unstable. Unstable means high energy. Matter will always want to go from high energy to a low energy, otherwise known as a stable state. Okay, lower energy means stable, not wanting to change. Unstable means wants to change. And the arrow will always go one way. You're never going to naturally, without any help, you're never going to go higher in energy. You can make it happen, but somebody's got to give. Like, I can make it go higher in energy, but only because I've given it. But if I just let it go natural on its own, it will always lower. Okay? Believe it or not, that's an important concept in chemistry when you think about the atoms and molecules, the protons, the electrons. We will refer back to that as we're understanding it, and things start to click if you have these foundations correct. All right, that is the end of this video. The rest of chapter 1 is mathy problem-solving type things, and I will save that for a separate video. So thanks for listening. Have a good day.